model batteries for different reasons. Sometimes just to gain some insights into how batteries work, and then maybe how batteries age.
What are some of the unresolved problems that you encounter on a daily, maybe weekly basis?
Inevitably, there's going to be coupling between electrical and thermal behavior. We always have this kind of experience that if you charge your phone on the stand, the phone gets hot, right? The batteries generate heat. In the context of system level simulation, we want faster speed of the simulation. The extreme conditions can be when the battery charge and discharge rate is very high. For high rate applications, for low temperature applications, and then for the scenario that we will be limited by the diffusion process, the equivalent circuit model runs into its limits.
All right, ladies and gentlemen, today I have an expert on battery modeling on the show. Xiangchun, welcome to the show.
Hi, Jousef. It's great to be here.
Did I pronounce your name correctly?
Yes.
First question? Okay, perfect.
Yes.
Excellent. Today we will talk about battery modeling, as I already said. So there's different types of models and different ways to approach modeling in the first place. So data-driven versus the physics-based approach. But before we jump into the nitty-gritty of battery modeling, can you give us a quick introduction to yourself and what are you working on at MathWorks?
Yes, sure. So my name is Xiangchun Zhang. I'm a principal application engineer at MathWorks. And my focus at MathWorks is on battery modeling and the BMS algorithm development. So BMS stands for Battery Management System. And I've been working in the battery space for about 19 years, ever since graduate school. So my journey on battery modeling, especially electrochemical modeling, started from graduate school when I started my PhD study for battery electrochemical modeling, where I incorporated thermal, electrochemical, and then structural mechanics into a battery 3D high fidelity model. So that's how all the journey started. And then after graduate school, I joined a company and developing solid state batteries. And then I joined MathWorks about 2.5 years ago. And at MathWorks, I help our customers understand how to use our tools for battery modeling and the BMS algorithm development.
Super interesting. So you've been working in the battery field for quite some time, especially when it comes to simulation and modeling. The question now is, okay, two maybe redundant questions, maybe dumb questions. Why would we model batteries in the first place? Why is it so important to simulate them? And then second question, you've been doing this for quite a while. Why haven't we solved battery modeling yet?
Right. So we model batteries for different reasons. Sometimes we model batteries just to gain some insights into how batteries work, and then how batteries age, right? So we all know that when we use our phones, and then after a few years, the battery doesn't last very long after full charge, and then you might need to charge more often. So how the batteries age is a question we can get some insights if we start building models. And then sometimes we model batteries just to design the batteries better, whether designing a battery cell or a battery pack better, right? So if we were like a battery manufacturer, we'll be into those detailed cell component designs. And then on the other hand, if we are like an automotive OEM battery pack designer, we're trying to figure out how many battery cells I need to put in the battery pack so that I can drive for certain range. And there are other reasons for modeling batteries. And for example, we want to provide a battery model so that we can use model and simulation to test our BMS algorithms. So those are the typical reasons why we want to model batteries. And regarding your second question, why we haven't solved batteries, batteries are a very complicated system. It can become like a multidisciplinary matter, and then also it can span across multiple scales. We can go all the way from atomistic scale simulations to battery pack simulations. So it's a multi-scale, multi-physics problem. And I think we are getting there. And then the thing is that we are still dealing with how to solve all the equations more efficiently with better speed, and then how to incorporate some of the newer mechanisms into our models. So that's a nutshell of where we are today.
Mm-hmm. Interesting. So we talked about modeling, and one of the sentences or quotes I always come back to is all models are wrong, but some are useful, from the British statistician George Box. Now the question is, what different types of model do exist, and which ones do you recommend to use, if there's even a recommendation? Maybe there's different types of applications, use cases, etc. So maybe you can give us some insights there.
Yeah. So based on my experience, I tend to divide battery models into three kinds of categories. The first one is electrochemical models, where we set up governing equations made of partial differential equations, or PDEs, to describe how lithium ions are being transported into the battery cell components, and some equations to describe how fast electrochemical reactions happen, right? So these kind of models we call electrochemical models. Then the second category of models is so-called data-driven models. Now, with a lot of connected devices available these days, we have a lot more data available, and then we have massive amount of data available. So we might as well just take advantage of this kind of data availability and then construct data-driven models. There's some other reasons why we want to do data-driven models. We're getting to them later, but that's the second category of models. And then the third category is some kind of in-between. So we call it equivalent circuit models, or ECMs, where we create an artificial circuit to mimic the dynamics inside the batteries. So the circuit is made of resistors, capacitors, and then we use this kind of dynamics of capacitors and resistors to mimic the lithium-ion diffusion and reaction kinetics inside the battery cells. So those are three kind of models. And when do we use them? How do we use them? Well, for electrochemical models, they are good for designing battery cells. They are good for understanding the fundamental mechanisms, good for understanding how batteries age. For data-driven models, and we can build the model based on the massive amount of data available. It doesn't necessarily require the expertise of electrochemistry, and it requires different kind of science, like data science specialty, right? And it can help us run the simulations faster, potentially, if we build a data-driven model. And then for the equivalent circuit model, ECM, it's good for system-level simulation. It's good for putting a model in our BMS, and then it's good for building a model to test our BMS. So those are the typical use cases for those three types of models.
I see. Very interesting. Maybe let's explain from a 0D to 3D perspective. What types of software do you provide, and how would you use them in the real world?
Yeah. So I'm like I mentioned at the beginning, I'm an application engineer at MathWorks. So at MathWorks, we provide a suite of tools called SimScape product family, and then SimScape is a tool that we use for modeling multi-domain physical systems. And then where we use blocks to model our physical systems. And then its strength is that coupling between multiple domains. So for instance, for battery systems, inevitably, there's going to be coupling between electrical and thermal behavior. We always have this kind of experience that if you charge your phone on the stand, the phone gets hot, right? The batteries generate heat. And then we also have this kind of experience that the batteries, they probably perform differently on a different temperature. So batteries can perform very differently on a cold day or on a hot day. So for those folks who have driven electric vehicles, you might have some experience, say, maybe the range will be different depending on the environmental temperature, right? So it's kind of important to model the electrical and thermal coupled behavior of batteries. So that's where the SimScape comes in. So SimScape is good for this kind of purpose, modeling like multi-domain physical systems. And then we can build a model to perform this kind of thermal and electrical coupled modeling. And the electrical behavior is basically captured by equivalent circuit model, or ECM we mentioned earlier. And then thermal behavior is captured by a lumped heat transfer thermal model. And then for some of the latest features we have, we can also support a height distributed thermal mass, meaning we can resolve the temperature gradient along the cell height direction as well. And we recently, and then earlier this year, we also started providing some capabilities in electrochemical modeling. We provided a model, so-called battery single particle block, which is a single particle model with electrolyte dynamics and the SPME in the industry. So we can talk about the details in a little bit, but those are the features that the tool provides.
Mm-hmm. What about 2D and 3D simulation? I mean, you talked about, Xiangchun, a little bit about the different scales, right? So would you then use 2D and 3D simulations for other types of scales that we're looking at? For example, a whole pack, for example?
Yeah, that's a good question. So some of you might know that MathWorks has another toolbox called Partial Differential Equation Toolbox, or PDE Toolbox. And then PDE Toolbox can enable us to model 3D thermal behavior of a battery cell or a battery pack, right? So for example, I can build a 3D thermal model using PDE Toolbox to describe the 3D temperature distribution within a battery cell or a battery module. And then I can perform some kind of model reduction or reduce order modeling, reduce the size of the matrices for the FEM algorithms, and then I can implement those reduced sized matrices into the SimScape environment. That way, the model can be calculated much faster, right? So how do we do that, the model reduction? Well, for the thermal conduction problem or heat conduction problem, we can do something similar to modal analysis. We can capture the fundamental modes of the thermal conduction, heat conduction, and by doing that, we can reduce the size of the matrices. And then with the reduced matrices, we can implement them in SimScape. So that way, we can do faster simulation. So now we have the thermal behavior in 3D captured by PDE Toolbox, and then incorporated into the SimScape environment with reduced matrices. Now we already take care of the 3D thermal part. And then for the electrical part, we still use the equivalent circuit model in the SimScape part. And then this way we can realize this kind of coupling where the thermal part is really high fidelity 2D, 3D model.
How is the solving being done? Is it being done sequentially? Is it kind of a co-simulation, or how does that work?
Yeah, good question. So in this case, because of that model reduction process, so we already captured the fundamental eigenmodes of the heat conduction problem. We have reduced the size of the matrices, and then we took the reduced matrices, and then we implement them in the SimScape environment. So in other words, the heat transfer or heat conduction is solved simultaneously by the SimScape and Simulink solvers at the same time when we solve the electrical behavior. So the PDE Toolbox, the functionality of PDE Toolbox is to define the 3D heat transfer problem, reduce the size of the FEM algorithms matrices, and then implement that into the SimScape environment. But once everything is in the SimScape environment, we can just solve everything simultaneously in the SimScape environment.
This is really interesting. How does it work, for example, when customers have an existing workflow where they use CFD or FEA software already? How would that integrate? How would the MathWorks library or the models integrate into an existing workflow like CFD or FEA workflows? Yeah,
that's a good question. So I think one way we can think about this is that, MathWorks tools, especially SimScape, is good for system-level simulation, right? And then it is kind of too costly if we want to integrate a 3D CFD or FEA into a system-level simulation. So in the context of system-level simulation, we want faster speed of the simulation, right? And then in this case, one way we can handle this kind of situation is that, well, we run a lot of CFD and FEA simulations, and then we generate a lot of simulation data. We use that simulation data to train a reduced order model. The reduced order model can be a machine learning or deep learning model. And then we use that model as some kind of reduced order version of the original CFD FEA model. And then we integrate that model with our tools and then SimScape or Simulink. So that's how we can bring CFD and FEA analysis into MathWorks environment for system level simulations.
Yeah. How does it actually work? Like, would I be able to work on a problem? Because I have no idea about this. So this is why I'm asking the expert. So would I be able to then export my model to a BMS system? Is that possible? And just test it on a test bench?
Yeah. So let's say, for example, I have a very high fidelity FEA or CFD model, and then through the procedure of reduced order modeling, and then the procedure looks like this. We run a lot of CFD and then FEA simulations. We generate a lot of simulation data for training purpose. And then with the simulation data, we can train a deep learning, most likely deep learning model, because in battery case, we need to capture the dynamics. So machine learning wouldn't be sufficient in this case. We needed to build a deep learning model to capture the battery dynamics. And then the premise is that the deep learning model will be able to simulate the whole system much faster than the original 3D CFD or FEA model for the battery system, right? So now we have a faster reduced order model based on deep learning, for example, neural nets, right? And now we can incorporate that into a system level model. For example, if I want to simulate the model together with a full vehicle, well, I have a faster model which was built based on the FEA or CFD analysis. And then I can integrate this kind of fast reduced order model or ROM with my full vehicle model simulation, right? So that's one use case. The other use case is like what you mentioned. I might want to use this kind of reduced order model for testing my BMS algorithms. And then, so in that case, I will connect my ROM with my BMS algorithms in the Simulink environment. And then we test our BMS algorithms in the simulation environment first, and then we can even deploy our ROM based on the FEA CFD, and then we can deploy the ROM to like a hardware in the loop testing a target hardware, such as speed code. So we'll get into those later, in the details of those later, but that's another way how we can test our BMS algorithms.
I see. But it wouldn't be necessary to run CFD or FEA simulations in order to have reduced order models. Would you also be able to run a SimScape simulation without FEA and CFD, and then from that data that you've accumulated, build a ROM? Is that possible?
Yeah, so I think, so the way we can build ROM, there are two ways we can generate the training data, right? One way is we can collect experimental data to build a ROM. Mm-hmm. And then we go to the lab, we perform a lot of experiments, and then we build a ROM. So that's one way. And then the other way is that we can run a lot of simulations based on high fidelity model, right? So high fidelity model can mean a few different things. My high fidelity model can be, say, a full 3D CFD or FEA model, and then that's one way of building like a high fidelity model. I can run a lot of simulations to generate simulation data for training my reduced order model. So that's one way of doing it. The other way of high fidelity model you can think about is that, say, in the SimScape environment, even though for every single cell is a 0D or 1D model, however, if you think about a battery pack that's made of hundreds of cells, if I have one of those models for each one of the cells, and then I consider this also like a high fidelity model, meaning even though for a single cell basis it's a 0D, 1D model, however, if I look at hundreds of cells within a pack, now that's a high fidelity model. And then this kind of high fidelity model would be able to get better simulation results for the temperature distribution among the whole battery pack, even though it's made by SimScape's technology. And then even though for every single cell, it is a 0 or 1D model, but if we look at from the pack perspective, it's a 3D model. And because like we are modeling the individual behavior of individual cells, this kind of model can also be very expensive depending on how many cells you have, right? Sometimes we have tens of cells in a pack, sometimes we have hundreds, and then thousands of cells in a pack.
I see. We talked about data-driven models, then you have the electrochemical models. What are some of the pros and cons from each of those, and how do they complement each other? And I think what would also be a very nice question, or maybe you can explain this to us, is when does it make sense to think about a data-driven approach in the first place?
Right. Yeah. So I say, obviously, the electrochemical modeling approach and data-driven approach, they require different expertise, right? So if we want to build an electrochemical model, we would require understanding of the electrochemistry, the physics, and then the physical processes, and then understanding how to solve PDEs. So that's the expertise requirement for building electrochemical models. Well, for data-driven models, it requires the expertise in data science. And we need to figure out how to organize all the data we have, and then pre-process them, and then make them ready and available for training a data-driven model, right? And then there's also the question that for data-driven model, what kind of model architecture do I want to do? And do I want to do a LSTM, non-short-term memory model, or do I want to do a neural state-space model, right? So those are considerations of the model architecture. And then there's also the question is that, say, well, for a model that's built, how do I deploy it? How do I use it? So these two types of models, they first require different expertise, right? And then sometimes in reality, teams, they work with what they have, the talents they have. So based on the composition of the team, people might choose different modeling technology. So that's the first thing. And then there are a lot of other considerations about the choices between those two technologies as well. And then just to name one among a few others, for example, say, can we understand all there is in terms of battery degradation mechanisms, right? So battery aging is a fairly complex process. And you probably understand that, say, there's going to be battery aging regardless. And then batteries will age all the time, whether through cycling or through sitting on the shelf. So there's cycling aging and then there's calendar aging. The exact mechanism for the aging can be fairly complex. And then if we really want to understand them, we probably need to do a lot of tail-down analysis, a lot of very detailed electrochemical tests to understand all the aging mechanisms. Well, so some of them we don't really understand very well. And then, so in this kind of case, well, there might be a case to be made. Say, what if we build a model and then based on the experimental data, we try to discover the complex patterns of how batteries age, and then is it possible that it will help us uncover certain things? So that's where the data-driven model can be very powerful. Help us uncover things that we haven't thought of, help us understand the complex patterns of battery aging behavior, and then most importantly say, well, when the physics-based model is struggling to describe the exact aging behavior, we just resolve to the data-driven approach. And then those are the considerations why we might want to consider a data-driven approach for battery modeling in the context of aging modeling.
That makes sense. What are some of the unresolved, quote-unquote, unresolved problems that you encounter on a daily, maybe weekly basis? Because I think there is some problems in the battery modeling industry or like segment where it's like the theory is maybe quite clear and concise, but from an application point of view, it's not that straightforward. Maybe you can talk about some of the things. You mentioned aging, but is there some other things that might be interesting to discuss?
So like say for battery modeling, and then let's take equivalent circuit model, for example, right? So equivalent circuit model is an approach where we construct an equivalent circuit made of resistors and capacitors to mimic the battery dynamics. Well, this kind of model has been very popular in the past 10, 20 years for system-level simulation, for BMS algorithm development, for testing BMS algorithms. And it's being widely adopted in the industry. However, the equivalent circuit model has its limitations because we are using a series of resistors and capacitors to approximate the dynamics, to approximate the diffusion process of lithium ions in the cell components. Well, this kind of approximation has its limits. It runs into limits, especially under some extreme conditions. The extreme conditions can be, say, when the battery charge and discharge rate is very high. So for high rate applications, for low temperature applications, and then for the scenario that we will be limited by the diffusion process, the equivalent circuit model runs into its limits, right? So that's one thing. The other thing is that there are certain dynamics that are associated with electrochemical reaction that's not really captured by equivalent circuit model. So therefore, the equivalent circuit model tends to be inaccurate for lower state of charge. So state of charge is an indicator of how much battery juice there's left in the battery cell. So sometimes we call it SOC, state of charge. So at low state of charge, equivalent circuit model can also run into its limits. So those are the limitations we have seen regarding the equivalent circuit model, right? People have tried to overcome those barriers and issues, limitations for the equivalent circuit model. by using various techniques. Right? So sometimes we might say, let's make all the resistors and capacitors rate dependent, in addition to be SOC and temperature dependent. So that's one way. And some people might say, well, if the physics-based model or equivalent circuit model fails, what if I do a hybrid approach, try to introduce some data-driven model to bridge that gap, right? So that's another approach. And then the other group of thought maybe say, okay, we have run to the limits of equivalent circuit model. It's time to start introducing electrochemical models. Being aware that electrochemical models, they can be very expensive to run simulations. And then just to bridge that gap in terms of simulation speed and fidelity, maybe we can do reduced ordered version of the electrochemical models by making some assumptions, make the equations simpler, and then instead of solving the full set of governing equations, we solve part of them by making some assumptions. So that's where the single particle model comes into play. So those are the limits and then limitations we have seen in terms of equivalent circuit models, how people might address that.
Mm-hmm. If I'm not mistaken, Xiangchun, in your doctoral thesis, you were incorporating also stress and strain into the simulation of batteries. The question now is, when does it make sense to incorporate this and when does it not make sense to incorporate this? Because when I think about batteries, there's hundreds, not even thousands of parameters that we can take into account. So how do you actually divide and conquer a problem? Let's say a customer comes to you and they say, we have a battery problem. And you're like, okay, where do I start? So how do you actually divide and conquer an approach and maybe evaluate if a structural analysis makes sense?
Right. So yeah, you're right. So in my PhD dissertation, I did a multiphysics modeling of batteries where the model considered heat generation, electrochemical kinetics, and intercalation-induced stress. So that's a structural mechanics problem. Mm-hmm. So the thinking behind that model is that, say, well, when I design battery cells, right? If you look at the lithium-ion batteries, and if you take it apart, and if you look at the active materials under the microscope or SEM, you will see that the battery active materials, they are made of particles, and then they have its 3D microstructure. Then the question becomes, when I design battery cells, like for those 3D structure, for each particle, how large do I want to make them? And then what kind of shape? Is it going to be like a sphere? Is it going to be ellipsoids? Is it going to be oblates? And then how large is good? The reason we want to consider this kind of question is that there are some trade-offs, right? So there are some considerations. So for the particles, if they are too wide and then too large, the diffusion process is too slow. The lithium ions is not going to diffuse into the particle very fast. So that's one consideration. The other consideration is the stress component. So imagine that when we intercalate lithium ions into a particle of active materials, the particle will expand. When we extract lithium ions out of the particle will shrink. So this kind of intercalation-induced stress and strain, expansion and contraction, is very similar to the situation we have in the thermal stress analogy. When the temperature changes, the volume changes, right? So there's going to be like an intercalation-induced stress and strain. So whenever there's like a cyclical stress and strain, the particle eventually will fail and break into pieces, and then it will cause failures. So now there's a question, say, how should I design my particle shape, size, and the shape so that I can minimize this kind of stress and strain due to intercalation, so I can prolong my battery life. So to summarize this kind of consideration for 3D microstructure design, mostly the users would consider them in the context of how I should design my battery cells, especially how should I design my battery active material size in terms of the particle shape and size. So that will be the primary interest to the battery cell designers.
I see. Yeah. But there's probably more to it, right? Depending on which glass you're looking for, which frame you're looking from. We talked about like the atomistic models, like then you go to maybe the macro scale, and then it really depends on the scale, I believe. But
correct.
For you in your day-to-day work, Xiangchun, how do you, for example, approach a problem? Like, do you have a specific system in mind, and how do you approach a modeling simulation problem? I think that would be interesting for the audience.
Yeah. So when I talk to our customers, and then the typical conversation goes like this: I would first understand what they want to build models for. Do they want to build models for estimating the range of an electric vehicle so that, say, they can understand for a fully charged battery pack for electric vehicle, electric car, how long it can drive? Is it going to be 100 miles, 200 miles, right? So in other words, the user is really want to build a battery model for system level simulation, for range estimation. And then some other user might say, I want to build a battery model where I can use it for my BMS algorithm development, right? So, and then some user might tell me, I want to really screen my battery design so that I can choose a particular battery design that's very suitable for my device. Then my device is so special, I only have so much volume for the battery cell, so that I want to really optimize all the volume there is and come up with a good battery choice. So depending on the use case and the scenario, and then the solution will be different, right? For the range estimation for electric car, we need to build a system level model. And then for a battery model that's going to be used for BMS, the emphasis is on accuracy and simulation speed. Well, BMS, most likely, the model is going to be deployed into a microcontroller. And then in that case, we cannot afford to run a very, very high fidelity model, which consuming a lot of computational resources. And then whereas if the question is, I want to screen through a few dozens of battery designs to come up with an optimal choice for my device, well, that has to do with battery design question. Most likely we have to deal with higher fidelity model, and then which will require electrochemical modeling components. So typically my conversation will be first understand what customers want to do with the model, and then try to triage, and then talk about the appropriate approach. Just to be sure, say, MathWorks tools, we don't support all the models. For example, we don't have an existing package, say, let's perform atomistic scale simulation. And then using MathWorks tools, we don't have an existing toolbox for this kind of functionality, for example. But we do have some functionalities for electrochemical modeling. So it's always, say, a great starting point to talk about the use cases. And then we can determine which kind of modeling strategy approach will be most suitable for the use case.
I see. I've had one of your colleagues on my podcast a couple of months ago, actually. We talked about physics-informed neural networks. Now, I would be interested in, you have the theory behind electrochemical simulations, all these different models, sometimes also models that people just came up with. When you do a data-driven approach, will the algorithm or the deep learning model be able to understand from the data what the physical boundaries are? Or do you give it explicitly some physical boundaries to be within some physical constraints?
Right. So first of all, I'm not an expert in physics-informed neural net, so I have some preliminary understanding of it. So my understanding of physics-informed neural net, or PINs, is that when we train a deep learning model, the loss function will incorporate the residuals of the governing equations of the physical system, right? So that's my preliminary understanding of PINs. And then for battery systems, and then like we have a set of governing equations and then PDEs, partial differential equations, mostly to describe the transport behavior of lithium ions inside the solid active material and the liquid electrolyte. We also have a Butler-Volmer electrochemical kinetics equation to describe how fast the electrochemical reaction happens. So we have like maybe 5 or 6 equations in total. Like most of them are PDEs, one algebraic equation, right? So in this kind of case, is it possible to train a physics-informed neural net to incorporate the residuals of all the equations into the loss function? I think it is possible. I haven't done it. It is very much possible. But what I have done is that, in terms of the data-driven model, is that I have built a model using a technology called neural state space. And then neural state space, some people call it neural ordinary differential equation, or neural ODE. Neural ODE has been used quite a bit in the deep learning world, and then maybe for image analysis and other things. But here, I used neural state space, or neural ODE, for modeling dynamic systems. Right? So imagine that I'm going to build a neural network to describe how my state evolves over time. So in the battery context, a state is like like for example, temperature is a state of charge is a state, right? State is a variable that indicates where my battery is at the moment. And then when we use a neural state space model to describe this kind of state space dynamics, first we build a neural net to describe the time derivative of the state variables. And then we build another neural net to describe how my outputs depend on the states. And then this way I construct a neural state space model. But under the hood, there are two neural nets to take care of the prediction of the state and then the output. And then I built a model, and then in this kind of architecture, or similar to this kind of architecture, to predict how the battery pack would respond to a current profile during a drive cycle scenario. Meaning, when I drive my vehicle on a highway, how my battery pack voltage and temperature will respond to this kind of velocity demand I have on a highway. So that's the neural state space model I have built. And I think when we build this kind of model, one thing we do need to keep in mind is that it's data-driven in nature, and then the model is as good as the data we provided to train the model, right? So there's always this question, is the model going to be able to generalize well? And then can we extrapolate, right? So for data-driven models, and then we need to be very cautious, and then we need to make sure that we don't try to extrapolate it too much, because there's no physics inside those neural nets. It's different from the electrochemical models. Electrochemical models, they are grounded in physical laws, so therefore it can extrapolate. But for this kind of neural net based approach, like a neural state space, we need to be cautious. In other words, we want to make sure that in the training process, we considered all the combinations of operating conditions, whether I want to drive the car on a very cold day in Alaska or on a very hot day in Arizona. So I need to consider all the operating temperature ranges in my training data.
That makes sense.
Yeah.
Is there kind of a rule of thumb when you want to take the path of a data-driven approach? How much data do we actually need in order to have an accurate result? Whatever accuracy means in this case.
Yeah, that's right. So let's say when was mentioned earlier, when we train a data-driven model, the training data can be from experiments. The training data can be from high-fidelity model simulations, FEA, CFD simulations, right? So sometimes this kind of training data can be very expensive to gather as well. If you do experiments, and then it is very expensive to set up this kind of experiments, and then it can be very time-consuming as well. For CFD simulations, FEA simulations, well, we have parallel computing for sure, but it also is kind of consuming a lot of resources. So, but we don't have much choice. We have to provide the training data that covers all the operating conditions, such as the temperature range, and then how fast I want to drive my car, meaning the rate I want to charge and discharge my battery, and then the state of charge range. So basically, the training data needs to cover the whole space, right? And then the rule of thumb would be, say, we want the training data to cover the whole operating range. And also, we want to make sure that the model we have trained for, then it can predict the battery voltage and temperature well under test data. So if we allocate some test data on the side, and then with the trained model, we want to test whether the model can predict voltage and temperature accurately with the test data, which was never seen in the training process. So that will be the ultimate test. So that will guide us in terms of whether we have collected enough data, whether our model is accurate enough. Right? So that's a data-driven approach. And then I'm not saying the physics-based model or electrochemical model doesn't require any experimental data. It requires experimental data. If you think about electrochemical models, there are a long list of parameters: diffusion coefficients, conductivity, reaction constants. So all those parameters, we need to figure out what they are. And it can take a combination of experimental approach and then parameter estimation. So by experimental approach, what I mean is that we go to the lab, we try to measure certain things directly. So chemists might be able to help us measure diffusion coefficient directly using electrochemical techniques. And then we might be able to measure conductivity directly in the lab. So that's a direct measurement of material properties. For the things that we cannot determine directly from experiments, we probably will resort to parameter estimation approach, where we do some experiments and provide some excitation to the system. We collect experimental data, and then we perform parameter estimation. So there is also a lot of work to be done to gather all those model parameters in the electrochemical modeling world.
This is super interesting. Yeah. You talked a little bit about the battery management system. What is the primary purpose of a battery management system? Because it has a lot of different purposes. And then we want to talk a little bit about the different BMS algorithms and what are some of the pitfalls when implementing these in Simscape, for example.
Yeah. So BMS, battery management system, you can think of is kind of like system to make sure that we use the battery most of all safely, and then second of all within certain operating range so that we can prolong the battery life. So safety is very important. We have seen cases where the battery is in a laptop, in a phone, or in a car catches fire. So safety is the most important issue for lithium-ion batteries. And so BMS is there to ensure that we always stay in the safety limits, right? Mm-hmm. So typical BMS algorithms, they will have a so-called overcharge, over-discharge, over-temperature limits. And then it makes sure that we don't over-discharge and the batteries, we don't overcharge the batteries. The battery temperature does not go very high or very low. So they are putting those like guardrails for safety purpose. So, and then there's also the functionality of try to prolong the battery life, right? Meaning, say, I want to be able to, say, use the batteries for longer time, maybe many more cycles, and then many more years. How do we achieve that? So it turns out that batteries tend to age faster under certain conditions. So therefore, if we try to avoid certain scenarios, try to make sure the battery operates in a happier region, and then we will be able to prolong the battery life. Let me give you a specific example. So you might have seen some of the smartphones. They will say, if you try to charge it overnight, and then it will charge to 80% and cease there. And then maybe you will charge the last 20% an hour before you wake up. So we have seen this kind of behavior, battery charging behavior on some of the phones. So that's exactly the purpose of BMS. Try to prolong the battery life by managing the operation of your battery. And so that's the second big category of BMS. So those are two main categories. One is ensure safety, safe operation. Two is prolong the battery life. Do those make sense to you before we talk about the other stuff?
Yeah, it makes definitely sense. I would have a follow-up question, which maybe kind of goes into the area of conspiracy theories. Is would a battery manufacturer be able to somehow predict within certain accuracy range how long the battery would last to make sure that before a new model, maybe of the iPhone comes out, that the battery life will be reduced by the time a new product comes out? Is that possible, or is that?
Yeah, so battery life very much depends on how you use the battery. And then, so different people might use different battery differently. So I might be only using my phone for answering phone calls. That's it. Mm-hmm. And then another people might be using the phone for watching YouTube videos of your podcast all the time. So it will be like different power demand. And then in that case, we will result in different battery life. So for the first category of usage, the battery might be able to last longer. For the second category, battery life is not that great. So I suspect that say anybody will be able to foresee how long the battery will last without knowing the typical user profile. And then that typical user profile can be a very, very wide range. And then therefore, I think say for the cell manufacturers, maybe what they can do is really try to design the batteries to encapsulate the wide range operations as much as possible. But then it still become like a very difficult and challenging task because even that range can be very different, right? And then the other thing is that they do tend to sometimes design different batteries for these different applications. Maybe the car batteries would be very different from the batteries you use for your smartwatch, for example.
I see. Okay.
Yeah.
Going back to the BMS now.
Yeah.
So, what are some of the pitfalls when implementing some BMS algorithms, like going from Simscape to the actual implementation? What could we do wrong as engineers?
Yeah. So I think some of the BMS functionalities, they are relatively straightforward to implement, like overcharge, over discharge, over temperature protection. Those are relatively straightforward. And then the challenging part can be the state estimations. Try to estimate battery state of charge, SOC, for example. So battery state of charge is an indicator of how much fuel there's left in the battery, how much juice there's left in the battery. You can consider it as a fuel gauge. In the automotive perspective, so for the conventional cars, we can measure how much fuel there is in the tank directly, right? But for battery pack, we cannot directly measure the state of charge. The only thing we can measure from the battery pack is temperature, voltage, and current. That's it. We cannot measure SOC directly. Well, then the question is, how do we use those measurable signals, such as temperature, current, and voltage, to estimate the state of charge? So to be able to accurately estimate state of charge has real-world implications, right? When I drive my car on the highway, I want to know how much juice there's left, how many miles there's left. I don't want to be stranded on the road, right? So there's real-world implications. So it's very important to accurately estimate state of charge with the measurable signals. And then that can be very challenging. And then the solutions we provide from MathWorks tools is that we provide a suite of tools for us to design BMS. And then for state of charge estimation specifically, we provided some library blocks built in Simulink for our users to estimate state of charge. So using some of the typical algorithms, whether Coulomb counting or extended Kalman filter or data-driven approach using a deep learning network. So we have this kind of blocks, and then they are implementing Simulink. And then what users can do is that they can first test those blocks in terms of robustness and accuracy with their own experimental data. And then if they are happy, they can start generating code, meaning automatically generating C and C++ code, and then deploy those state estimation codes to their microcontrollers. And then the way our tools can help us is that the whole process is well streamed. We have toolboxes starting from capturing the requirements of the BMS to implementing the algorithms, testing the algorithms, automatically generating the code, and then testing them again, and then to figure out whether the original requirements are met. So we have a whole suite of tools. So the reason we have all this is that a lot of our customers, they need to pass certain certification. So they need to have everything well documented. Imagine that if I want to put batteries in a car or in a electrical aircraft, right? So there's going to be certifications, and then we need to pass certain certification process. So we need to document everything we have done. All the requirements are met. So we have tools to help our customers to prepare for this kind of certification process by showing that what are the requirements, what tests we have done, and what are the outcomes of our tests. So those are the typical challenges, and then how our tools can support our customers.
This is super interesting. Thanks for sharing, Xiangchun. Regarding the software development for the C and C++ code, would people or engineers also be able to code inside of the MATLAB environment or MathWorks environment, whatever tool they're using, and then deploy it immediately to the BMS, for example?
Yeah. So good question. So we first of all, we do have some customers who prefer to hand code in C and C++. Yeah. But most of our customers, the way they like to use our tools is that, they first develop the BMS algorithms, such as SOC estimation, using our tool, a tool called Simulink. And then In the Simulink environment, you can implement your algorithms using blocks, right? And then once you have the BMS algorithms implemented in Simulink, and then you can start testing them. And once you're happy with the results in terms of accuracy and robustness, most likely the implemented algorithm in Simulink will be able to support automatic code generation. Meaning, with a click of a button, you can generate C and C++ code automatically after that Simulink block. Now, then the first question is that, well, is the generated C code equivalent to my Simulink model in terms of the algorithms? Are they equivalent, right? So we can do the equivalency test, make sure the generated code is indeed the algorithm I intended to check the equivalency. Once that's checked, then we have confidence in the generated C code that, okay, now we are ready for deployment and then further testing. So the strength of our tool is that automatic code generation part. Once you have implemented the algorithm using some kind of like a very user-friendly block diagrams, you can automatically generate C code. I believe not everybody is kind of very comfortable writing C code from scratch. So this kind of automatic C code generation help us move very fast, much faster in our development process.
This is really cool. I like that a lot. Yeah, maybe because we're approaching the end of the podcast, I think we can link some resources in the description so people can check it out, how they can get help using some automatic code generation. What are some of the future technologies or BMS developments that you foresee in the next 3 to 5 years?
Right. Yeah. So I think first of all, for the battery technology in general, I think people want batteries that are much cheaper and then has longer range or runtime, in other words, higher energy density, and then also much safer, right? We are concerned about battery safety as always. So for the future battery technology, we need to improve the safety. We need to increase the energy density. We need to reduce the cost. So, reality is that the battery cost has come down quite a bit in the last 10, 20 years, and then maybe more than tenfold. And then, so it has come down quite a bit, but it will be better if we can reduce the cost a little bit further. And then for safety, and then people are starting to work on very actively on the solid state battery technology. And then in which case we replace the liquid electrolyte with solid ceramic electrolyte, for example. And in that case, we remove some of the flammable materials from the lithium-ion batteries by replacing the liquid electrolyte with solid electrolyte. So that will enhance the safety quite a bit. And then there are a lot of ongoing development work by a lot of battery manufacturers and also automotive OEMs in this area. That's the trend we are seeing here in the market. And energy density, well, people are trying to come up with new chemistry that are more energy dense to make the batteries more energy dense. Okay, so that's the trend we are seeing in the battery technology. From the BMS perspective, I think we are blessed that in the sense that now we have more and more computing power that's available to us. And then in the context that maybe we will have more powerful centralized processors on board a vehicle, or maybe we can really tap into the availability of cloud computing. So this kind of powerful computing resources opens the door to a lot of other things from the BMS perspective, meaning we now can afford running more complex high fidelity models, like electrochemical models, and we can also afford to run more advanced BMS algorithms for state estimation, for other things. And then what this also means that now in the cloud, maybe we can start building a digital twin to help us understand the battery behavior in the future, to help us detect anomaly, to help us optimize that battery operation further. So that's a digital twin element. So I think those are the trends we are seeing in the market. And then that's soon to come in terms of the BMS.
Mm-hmm. In terms of deep learning models and anomaly detection, is there already something that people can use from the MathWorks suite where they can just detect anomalies, for example?
Yeah, so MathWorks, we have a toolbox called Predictive Maintenance Toolbox. So Predictive Maintenance Toolbox has certain features for us to detect anomalies in any real-world physical systems. And then we started having some battery-specific features to help us extract features from battery data, such as incremental capacity, differential capacity, and voltage, and things like that. So this kind of extractive feature from the battery data will help us better understand how batteries are operating, and then it will pave the way for us to detect anomaly further. So those are the battery-specific features. But overall, predictive maintenance is great at anomaly detection, and it has been used in the industry for other systems. And we're just starting to look at battery systems, start having some features for battery-specific purposes.
Mm-hmm. That is really interesting. Is there anything that I haven't asked you, Xiangchun, in this podcast that you would like to talk about to the audience about batteries? Something that we have missed, maybe?
Well, I think we have covered everything. What I just want to recap is that, there are a wide range of battery models we can implement. They all depend on our use cases. And then what MathWorks tools can provide is that we can, for most, build models for running system-level simulations, for BMS algorithm development, for testing our BMS algorithms, for optimizing our battery pack designs. And then also, MathWorks tools can help us develop BMS algorithms, test BMS algorithms, and then even test BMS algorithms under faulty conditions. When there's a fault in the battery, we can test it as well, which is very challenging to do using real-world physical batteries. So those are the main capabilities MathWorks tools provide. And then with that, I think I want to thank you for the opportunity to speak with you today.
Thank you so much, Xiangchun. I certainly learned a lot. Unfortunately, we only had 1 hour to talk about battery modeling and about battery systems, but I think maybe there will be a second part in the future. Who knows? But again, thank you so much.
Yeah, thank you for having me.